So, regression analysis is a tool to help us answer questions. Namely, we are going to be studying the relationship between variables. For example, how does education affect wages? Or how does education affect health? Or how does marriage affect health? All of these questions could be answered with regression analysis. If we want to look at how education affects wages, we would simply estimate the following equation. And this is just the equation of a line, where the wage is our y variable and education is our x variable. The alpha is our y-intercept, and the u is called the error term. And the error term contains all the other things that affect wages besides education. So through regression analysis, we're going to estimate the alpha and the beta by finding the line of best fit through our data points. So I won't get into what best fit means, but let's just say that we are trying to get as close to the actual data as we can with our estimated line. So in this case, beta, which is the coefficient on education, is a slope. It tells us how wages change when education changes. Usually we'll say, okay, when education goes up by a year, then what happens to wages? Here's a graphical representation of what we're doing. So I have wages on the y-axis and years of education on the x-axis. And all those little circles represent actual data points. So data we've collected from individual people on their wages and years of education. And the line we're estimating is also drawn through the data. So obviously, because just by looking at the circles, we see that there's an upward slope, then we know that when we estimate our regression, that line is also going to have a positive upward slope, which makes sense because we think that as years of education increase, so do wages. So here is the results of a regression that I have run in a statistical package using some real data. So I have data on over 6,000 people, and what we see when we get the results, we see a column called coefficient, and those are the estimated alpha and beta. So when I write out my results, I do so, as I have for you already, in the orange rectangle, predicted wage. It has a hat over it to indicate that we have predicted the regression is equal to negative 30,841 plus 5,015 times education. So basically what that tells us is that when education goes up by a year, predicted wages will increase by $5,015. Here I'm measuring wage as annual salary. Okay, so if I wanted to predict what expected wages would be for someone who has 10 years of education, I would simply plug in 10 for education, and out would pop an estimated wage. So you would do the calculation as follows. And you would plug it into your calculator, negative 30,841 plus 5,015 times 10 and out would pop an estimated wage for someone who has 10 years of education. Something else I wanted to mention is called goodness of fit, or R-squared, and that can be found on the regression results right here, R-squared. So R-squared simply tells us how much of the variation in wages are explained by the variables in our model, in this case, education. So if I asked you to interpret an R-squared, you would simply say that 13.6% of the variation in wages is explained by years of education. So basically we have all this data on wages, and obviously there's some variation in wages because everyone has different wages and many people have different levels of education. So education explains about 13.6 of the variation in wages that we observed. So obviously there are other variables that we're not accounting for that explain the other 100 minus 13.6% of the variation in wages. The other thing to briefly mention about these regression results are called t-statistics, and those are found in this column here. And basically, without getting into too much detail, if you have a test statistic or t-statistic that is greater than 2 in absolute value, that means that that particular variable is statistically significant and should be in the regression. So in this case, education has a t-statistic of 31.1. That's very large, and that means that education definitely impacts wages and should be in this model. I'm not going to talk about the constant at this point in time because every regression we estimate has a constant, and the t-statistic on that constant is not that important. Okay, another common model that we see is the following. The natural log of my y variable is equal to alpha plus beta times my x variable. So here I have the log of wages as a function of education, and I've run the regression using the same data that we had before. I have my coefficients, and I've written out my results, where the predicted log wage is 8.4 plus 0.13 times years of education. When you have a log on the left-hand side, the way to interpret the results is to say that when education increases by 1 year, then wages will increase by 13%. So what you would do is take the coefficient on education, talk about it in terms of a percent, but you have to move the decimal place. And that way of interpreting it is because of the properties of logs. So when education goes up by 1 year, wages will go up by 13% on average. So here we also have a log wage model, but instead of including just education, I've included a bunch of other variables that might also affect wages. So I have tenure, which is years of tenure on the current job, and then I have male, white, and married. And these are called dummy or indicator variables because they capture information that is not quantitative. It's actually qualitative. So a male dummy variable would be equal to 1 if you're male and equal to 0 if you're female. A white dummy variable would be equal to 1 if you're white and 0 if you're non-white. A married dummy variable would be equal to 1 if you're married and 0 if you're not married. So I've run a regression using these variables, and I found the following results. You can look down the row or the column that says coefficient, and why don't we practice interpreting one of the dummy variable coefficients. So let's look at the coefficient on male. It is 0.549. So the way to interpret it is as follows. Males earn 55% more than females, holding all these other variables constant. Now that seems like a really big number, and in real life it is very big. So typically we don't find that men earn 55% more than women. So I am just going to attribute that to the fact that I probably haven't estimated the best model of wages that I can. I probably should include a lot of other things in my model because there are many other things that affect wages. So let's talk a little bit about the power of multiple linear regression. And multiple linear regression is simply when I'm including multiple x variables. So not just education, but I've included tenure, male, white, and married. If we are interested in the effect of gender on wages, then we say that we're controlling for these other variables. So we're controlling for education, tenure, race, and marital status. And the idea behind this is that it's similar to what a scientist does in the lab. So if a scientist is interested in the effect of a drug on rats' sleeping patterns, that scientist can control for many other factors in the lab, like the amount of daylight or the amount of food that the rats get, and so on. In real life, we don't have control over people, but the equivalent of controlling for these factors is to include them in our regression. So we might say that among all the people with the same education level, men earn 55% more than women. So here's another example. We're going to be looking at 60 NFL quarterbacks. We have 3 variables: touchdowns, number of touchdown passes thrown, attempts, number of passes attempted, and completions, number of passes completed. And we want to know how attempts and completions affect touchdowns. So here is a regression result using real data, and here I'm only looking at how attempts affect touchdowns. So I have estimated touchdowns equals negative 0.28 plus 0.037 times attempts. So how many more touchdowns is a quarterback expected to get if he throws 100 more passes over the season? Well, if attempts goes up by 100, then touchdowns would go up by 3.7. So there I'm just multiplying 0.037 times 100, an increase of 100 attempts to get 3.7. So here we see there's a positive relationship between the number of attempts and the number of touchdowns. Now, if I add completions into the model, I find the following. Touchdowns is equal to 0.025 minus 0.031 times attempts plus 0.116 times completions. All of a sudden, the coefficient on pass attempts is now negative. So what's going on? Well, the answer is we've added completions. So the way to interpret that coefficient on attempts is to say, okay, if I hold completions constant, but attempts goes up, what am I really saying? So hold completions constant. I allow attempts to change. In this case, let's say attempts increase. What does that mean? Well, that means that my completion rate is getting worse. It's falling. Right? That's a bad thing. And so that's why the coefficient on attempts is negative. The coefficient on completions is positive. So the more completions I have, no matter how many attempts, holding those constant, the more completions I have, the more touchdowns I have. The more attempts I have, holding completions constant, the fewer touchdowns I have, because it really means my completion rate is falling. Okay, a few more things I want to mention. Causation versus correlation. What does that mean? Let's look at a few examples. So numerous studies show that children who eat a healthy breakfast perform better in the classroom. Can we conclude that a healthy breakfast improves classroom performance? So what we're saying is that we find a correlation between children's healthy breakfasts and their classroom performance. But can we conclude that a healthy breakfast actually causes classroom performance? In this case, the answer is probably no. We cannot conclude that a healthy breakfast improves classroom performance because there's probably something else going on here that could both cause improved classroom performance and also cause children to have a healthy breakfast. So one of those might be parent education. So if parents are more educated, parent education could lead to a healthier breakfast. And higher parent education could also lead to better classroom performance by children. So economists are always trying to prove or reach that goal of showing causation, but in many cases, without more sophisticated techniques, all we can show is correlation. So here's another example. Suppose we estimate the following model and we find that an additional drink is associated with $1,000 of income. Does this mean you can boost your earnings by drinking more alcohol? So here we see that earnings are a function of alcohol. Does it even make sense that if you drink more, your earnings go up? I'm going to argue that no, it probably doesn't make much sense, although you might be able to come up with an argument. What I would argue is going on here is something called reverse causation. Basically, earnings affect alcohol? So by estimating this model, earnings as a function of alcohol, we are hypothesizing that alcohol affects earnings. Probably the other way around is more reasonable, that earnings affect alcohol consumption. The more you earn, the more money you have to buy alcohol. So even if we estimated the model with earnings as our y variable, and we found a positive relationship, that is simply correlation. It's not causation. Okay, one more example. Going back to that original wage model where wages are a function of education, can we say that education causes wages so that when education goes up, wages go up? Well, we always find a positive correlation between the two, but there might be some other factor that directly affects education and earnings that we're not including in the model. So one common example that we see is that ability is part of the error term. And we think that ability is positively correlated with education because if you're more able, then it's easier for you to get an education. But we also think that ability affects wages. Sometimes we just don't have the data to control for ability. In fact, ability is hard to measure, but sometimes people use like an IQ score as a measure of ability. But often we just don't have that data, and so that's going to impact our results. It's going to be hard for us to get a good measure of causation. How does education cause wages? So just to summarize, we ideally want to know, does changing X cause a change in Y? We usually can't prove causation. Oftentimes, if we find a correlation, that may reflect what's called common response, and that was the example with the healthy breakfast affecting performance. We saw that parent education might affect both of those things. Reverse causation is a very common problem. So we find that Y might actually affect X and not the other way around. And then in the last example with ability, that's called unobserved heterogeneity or omitted variable bias. We're not including something in the model that really should be there and will help us get a better estimate. And all of these things are common problems that need to be addressed if it's going to be a serious regression analysis.